Welcome to the Deep Dive. Today we're unlocking the secrets of a really foundational technology. It underpins precision manufacturing everywhere. Computer numerical control, or CNC controllers. Our mission here is to, well, cut through the complexity, show you how these brains of modern machines actually operate, why they're so critical, and where they're heading. Think of this as your shortcut to understanding what really goes on behind the scenes of precision manufacturing, from tiny chips to, huge airplane parts.
Absolutely. And our guide for this exploration comes from the extensive publications and articles of Arthur Hovsepian. He's an expert who's really spent years deep in this field, so his insights give us a very solid, practical understanding of these controllers.
Right, so have you ever really stopped to wonder how we get such incredible precision these days?
Yeah.
How parts are made identically, down to microscopic levels again and again. It really all comes back to this unsung hero, the CNC controller. This tech isn't just important, it's the pivot point for accuracy, efficiency, automation,
Yeah.
everything in machining. It's that crucial link turning a digital design into a perfect physical thing. Let's start with the why. Why are these things not just useful, but absolutely indispensable today?
Well, it goes way beyond just being a neat piece of tech. CNC controllers are really the competitive edge in today's market. It moves so fast. They're the absolute heartbeat of automated machining. They enable levels of precision, efficiency, repeatability, things that just weren't possible before. Trying to compete without them today be like trying to navigate London with just a paper map. You'd get left behind fast.
Right, totally outmatched.
And their importance just skyrockets when we talk about Industry 4.0. For anyone not familiar, Industry 4.0 is basically the fourth industrial revolution. It's driven by digital tech, the Internet of Things, IoT connecting machines, basically smart manufacturing. CNC controllers are right at the center because they allow that direct, real-time communication between machines, systems, even people.
That real-time data exchange sounds like it completely changes how a factory floor works. Can you give an example? What does that connection actually do?
Oh, it's transformative. It's not just about things being a bit faster. Think of the factory floor becoming like a self-optimizing organism. Machines aren't just blindly making parts. They're watching their own performance, predicting maintenance before a breakdown.
Predictive maintenance.
Exactly. And dynamically optimizing their own operations, all on the fly. This kind of connection, it cuts downtime massively, makes everything way more efficient, more responsive. It's about building intelligent systems that adapt.
That is a huge leap from older methods.
Mm.
So practically speaking, how do these controllers take complex CAD data and turn it into actual cuts, drills, milling?
Yeah, their ability to interpret that geometric data precisely is what leads directly to better product quality and much less waste, better material use. They're way beyond simple cuts now. CNC controllers are essential for advanced stuff like additive manufacturing, think industrial 3D printing, and multi-axis machining.
Things needed for really complex shapes, right?
Exactly. Complex geometries, custom parts, incredible detail. This flexibility means manufacturers can react to market changes super quickly, almost on demand.
So zooming out, for a business, this is all about competitive advantage.
Absolutely. Fundamentally. Companies using CNC tech properly can make high-quality parts efficiently. That means lower production costs, faster delivery times. It makes businesses incredibly agile, and like you said, that flexibility is key. Reprogramming for different jobs is relatively easy. That's just not something you get with traditional rigid machining where changing tools might take ages.
Okay. I get the why. It's indispensable. Now let's click behind the curtain. How does that digital blueprint actually become a physical thing? What's the step-by-step?
Right. So the whole thing kicks off with creating a precise geometric model, usually in CAD software computer-aided design. Then you've got CAPP, computer-aided process planning, which figures out the best steps, and CAM, computer-aided manufacturing software. These work together to decide the machining strategy, pick the right tools, set speeds, feed rates, all those critical parameters.
Got it. CAD designs it, KPMEC plans how to make it.
Exactly. And the key output from all that planning is something called G-code. Think of G-code as the standard language CNC machines speak. It's basically a text file, full of commands defining tool paths, operations, even things like turning coolant on or off.
Just lines of text commands.
Yeah. For simple stuff, a skilled person might even write it by hand. But for complex parts, it's almost always software generated.
And this is where the CNC controller steps in, right, as the interpreter.
Precisely. It receives that G-code, understands it, and meticulously translates it into the exact electrical signals that guide the machine tool's motors. It's the critical bridge.
Okay, fascinating. Now let's get into the hardware, the physical bits. What are the nuts and bolts inside one of these controllers? If we cracked one open, what would we find?
Okay. At its heart, a CNC system has several key hardware bits working together. First, the processor. This really is the brain. Depending on the job, it could be a small microcontroller for simpler tasks, maybe like an engraver. Or it could be a powerful industrial CPU running a whole multi-axis production line. For really high-end stuff, you might even see FPGAs, field programmable gate arrays. Super fast, super customizable.
FPGAs. Those are reconfigurable chips.
That's them. And often these processors run on a real-time operating system, an RTOS. That guarantees things happen immediately when they need to. Critically important. And obviously memory. You need memory to store the programs and working data.
Makes sense. Brain, operating system, memory. What else?
Next up is input-output, or I/O. Think of this as the controller's senses and its hands. Inputs are things like sensors, limit switches. They feed information back to the controller, like the safety door is closed or the axis has reached its limit.
So the controller knows what the machine is doing.
Exactly. And outputs are the commands going out from the controller to motors, the spindle motor, coolant pumps, things like that. This I/O is crucial for that real-time monitoring and control. It's a constant conversation.
Okay, senses and actions. Got it.
Then you have communication ports. These are the digital highways connecting the controller to everything else. The computer you program it from, the motor drives, other peripherals. They use specific protocols like EtherCAT, CAN, Modbus, basically high-speed digital languages to make sure everything is perfectly synced down to the microsecond. Fast, reliable data exchange.
So everything talks the same language quickly.
Pretty much. Fourth is the human-machine interface, the HMI. This is how the operator interacts with it all. Displays, touchscreens, keyboards, buttons. It lets you load programs, tweak settings, see what the machine's doing in real time. Your control panel, essentially.
The dashboard.
Exactly. And finally, but absolutely critical, is a stable power supply. It has to provide clean, consistent power to all these sensitive electronic components. Without good power, nothing else works right.
Right. Can't forget the power. Okay, so we have all these parts. Processor, I/O, comms, HMI, power. How do they work together? How is it orchestrated?
Yeah, it's not just a random collection of parts. Functionally, a CNC system is usually thought of in three main cooperating units. First is the numerical control kernel, or NCK. This is the real core engine. It processes the part program, the G-code, calculates the toolpath, controls the precise axis positions. It's the motion brain.
NCK handles the movement.
Correct. Then you have the man-machine interface, the MMI, which we just talked about. That's the user interface layer, showing status, letting you edit programs, adjust things, the operator's window. And third is the programmable logic controller, or PLC. The PLC manages the logical sequence of all the other machine functions, the non-motion stuff.
Like what?
Like automatic tool changes, clamping the workpiece, turning the spindle on or off, managing coolant flow, all the background tasks that need to happen in the right order.
Okay, so NCK for motion, MMI for the operator, PLC for everything else.
Got it.
That sums it up well. And these units, they might be on separate physical boards, or especially in modern controllers, they might all run on one powerful processor using that RTOS we mentioned. They talk to each other over high-speed internal connections or buses.
So the software running on these, particularly the NCK, that must be incredibly important for turning the G-code into actual, precise physical movement. Oh, absolutely crucial. The NCK software is where the magic translation happens. It orchestrates this complex sequence of steps. First is program interpretation. The NCK reads the G-code, line by line. It figures out the commands, processes parameters like feed rate, spindle speed, the type of movement needed.
Translating the G-code language.
Precisely. Then it moves to toolpath generation. The software calculates the exact path the tool needs to follow. This includes all the intermediate points for curves, arcs, and it applies vital compensations, like adjusting for the tool's physical size, its radius and length. It might even compensate for tiny bits of thermal expansion in the machine itself.
Wow, that detailed.
For high precision, yes. Then you can't just instantly start or stop moving, right?
No, things would jerk around.
Exactly. So the next stage is motion profile generation. The NCK creates smooth acceleration and deceleration curves for every move. This ensures fluid, safe motion without vibrations. Advanced controllers use look-ahead algorithms here. They read ahead in the G-code to anticipate sharp corners or changes in direction and smooth the transitions.
Planning ahead for smooth moves.
Yep. Then comes interpolation. This is where the controller coordinates multiple axes moving simultaneously. To make the tool follow the planned path perfectly, whether it's a straight line, a circle, or a complex curve like a spline, it synchronizes the movement of, say, the X and Y axes to create a diagonal line or an arc.
Getting all the motors working together.
Perfectly together. And the final step in the NCK software is axis control output. This is where the calculated target position data for each individual motor drive is sent out. Commands for position, speed, maybe even acceleration. The lower level motor controls then execute these commands.
That is an incredible amount of calculation happening, constantly in milliseconds.
Oh yeah. These stages run in incredibly short cycles, often a millisecond or even faster. It needs huge computational power. And that's why the RTOS is so vital. It guarantees these critical calculations happen on time, every time. No delays allowed.
The NCK really is that bridge from the digital plan to the physical reality.
It absolutely is. And for top-tier accuracy, CNC relies heavily on closed-loop control systems. Think of it as constant feedback and correction.
Like it's always checking its own work.
Exactly. There are usually 3 main feedback loops working together super fast. There's the position loop. It uses sensors and coders to measure the actual position of the axis and compares it to where the NCK told it to go. If there's an error, it corrects it instantly.
Like GPS correcting your route.
A good analogy. Then there's the velocity loop. It checks the actual speed of the motor against the desired speed profile from the NCK. It adjusts the motor power to keep the motion smooth and accurate, like a very precise cruise control. And closest to the motor itself is the current loop. This controls the electrical current going into the motor windings very precisely. That directly controls the torque, the twisting force the motor produces, ensuring it has just the right muscle for the job at every moment.
Position, speed, and power all constantly checked and adjusted.
Simultaneously and seamlessly. And again, the RTOS is the conductor making sure all these loops run perfectly on schedule without interfering with each other.
Okay, this technology is clearly incredibly sophisticated already. So what's next? Where is this heading in the future? How do CNC controllers keep evolving?
Well, we're seeing some really significant trends emerging. Definitely more integration with the Internet of Things, IoT, machines becoming smarter nodes in a bigger factory network, sharing data, coordinating better.
The connected factory idea again.
Exactly. We're also seeing a big rise in AI-based predictive maintenance, using artificial intelligence to analyze machine data and predict failures before they happen. That saves huge amounts of money and downtime. And there's a strong push towards sustainability. CNC plays a role here too, optimizing tool paths to use less energy, minimize waste material.
Makes sense, using resources smarter.
And a really big one, highlighted in Arthur Hovsepian's work, is the growing role of AI directly in CNC programming and operation. This could be revolutionary. AI offers huge advantages over traditional methods.
How so? What could AI do differently?
Imagine machines that don't just execute G-code, but learn from each part they make, refining their own process for a better quality or speed. AI could potentially automate G-code generation in smarter ways, optimize cutting strategies on the fly based on real-time sensor feedback, adapt to tool wear or material variations automatically.
So the machine starts making decisions itself, based on learning.
That's the potential, yes. It's a core part of making manufacturing truly smart. There's a lot of research globally focused on making this AI integration practical and effective.
That paints a picture of CNC systems becoming much smarter, more efficient, more connected. More autonomous, maybe?
More autonomous in optimizing their tasks, certainly. It's about leveraging data and intelligence for unprecedented performance.
Wow, so what an incredible journey we've taken. From just a digital file to amazing physical precision, all driven by this complex dance of hardware and software inside the CNC controller. It's so clear how foundational they are for modern manufacturing, for Industry 4.0.
Absolutely. And really grasping these core principles, the kind Arthur Hovsepian has detailed in his work, is just essential. It's key for anyone looking to really leverage CNC technology effectively today, and certainly for driving the next wave of innovation in this field.
Totally agree. Which leads to a final thought for you, our listener. Imagine a future where one digital idea, maybe refined by AI, can be flawlessly made real by intelligent machines anywhere on Earth. With incredible speed, accuracy, constantly learning, what kinds of new possibilities does that open up for innovation, for customization, in practically every industry you can think of? Something to ponder. Thank you for joining us on this deep dive.